Hey everyone, and welcome. Today we're tackling Leetcode problem 2536, Increment Submatrices, by 1. This problem is a fantastic example of how a clever trick can turn a slow, obvious solution into a super efficient one. Let's break it down together. Alright, let's look at the goal. We start with a square grid, or matrix, of a given size n, and it's completely filled with zeros. We're also given a list of instructions called queries. Each instruction defines a rectangle using its top left and bottom right corners. Our job is to follow every instruction, adding 1 to all the numbers inside each rectangle. When all the instructions are done, we return the final grid. So to put it simply, we're given a blank canvas of zeros. Then, we get a series of commands, each telling us to paint a specific rectangular area by adding 1 to it. The final picture, which is the grid with all the updated numbers, is what we need to return. Let's walk through the first example to make this concrete. We have a 3x3 grid of zeros. The first instruction tells us to update the rectangle from row 1, column 1, to row 2, column 2. So we go through that bottom right 4-cell area, and add 1 to each cell. Pretty straightforward so far. Now for the second instruction. It says to update the rectangle from row 0, column 0, to row 1, column 1. We take our current grid, and again add 1 to every cell in this new area. Notice that the cell at row 1, column 1, was part of both rectangles, so it gets incremented twice, ending up with a value of 2. And that's our final result. So the first idea that probably comes to mind is the brute force method. For every single query, we can run a nested loop to visit every cell inside its rectangle, and just add 1. This works, but it's very inefficient. Imagine a huge grid and thousands of queries that overlap. We'd be visiting some cells thousands of times. There has to be a faster way. And there is. The efficient solution uses a concept called a 2D difference array. Think of it like this. Instead of painting the entire rectangle for each instruction, what if we just put markers at the corners? Then, at the very end, we can do one final sweep over the grid to calculate the final values based on all the markers we've placed. So how do these markers work? Let's say we want to increment a rectangle. First, at the top left corner, we place a +1 marker. You can think of this as starting a wave that adds 1 to everything below and to the right of it. But that wave goes on forever, and we need it to stop at the rectangle's boundaries. So just outside the rectangle's right edge, we place a -1 marker. This cancels out the wave for everything further to the right. We do the same thing just below the bottom edge, to cancel the wave downwards. There's a small catch. The area to the bottom right of our rectangle has now been cancelled twice. To fix this, we place a +1 marker at that corner to counteract the double negative. It sounds a bit complex, but it means every single query, no matter its size, only requires 4 simple updates. Okay, so we've processed all our instructions and our difference grid is full of these +1 and -1 markers. How do we turn this into our final answer? We use a method called a two-dimensional prefix sum. We'll build our final matrix cell by cell. The true value for any cell is simply the sum of all the markers that came before it, both from above and from the left. The formula looks a little scary, but the idea is simple. To find the value at any spot, you take the marker value at that exact spot, add the final value from the cell directly above it, add the final value from the cell to its left, and then you have to subtract the value from the diagonal top left cell. We do this because that diagonal part was counted in both the above sum and the left sum, so we need to remove one of them to avoid double counting. Just a quick heads up. We'll be walking through the solution using Python, but don't worry if that's not your main language. The logic is exactly the same everywhere. I'll be showing the full code for other popular languages like Java, C++, and JavaScript towards the end of the video. Okay, we've talked about the big picture and the logic. Now let's see what this looks like as actual code. I'll put the full solution up on the screen first. And don't worry, after that, we'll walk through the most important sections together. Alright, here's the Python code for our difference array approach. It might look a bit long, but it's really just 2 main parts which we'll break down right now. First, we create our difference grid. Notice we make it size n+1 by n+1. This is a common trick that saves us from writing extra if statements to check if we're at the edge of the grid. It makes the code cleaner. Then, we just loop through every query. For each one we perform those 4 marker updates we talked about. This part is super fast, as it doesn't depend on the size of the rectangles. In the second half, we create our final matrix. Then, we loop through every single cell to calculate its final value. The code here is a direct translation of the prefix sum idea. The value at the current cell is its own marker value, plus the final value from above, plus the final value from the left, minus the final value from the diagonal top left. The code in the previous slide optimizes this by handling the first row and column as special cases before doing the main loop. So let's talk performance. For time complexity, we have two parts. First, processing all the queries. If there are Q queries, this takes time proportional to Q. Second, we have to build the final n by n matrix, which takes n squared time. So the total time is big O of n squared plus Q. For space, we need that extra difference grid to store our markers, which is the same size as our original grid, so the space complexity is big O of n squared. Alright, that covers the main solution in Python. As promised, for those of you who code in other languages, I'm about to show the full solutions for Java, C++, and JavaScript. I won't be breaking these down, so just pause the video on your language of choice to check it out. Alright, as promised, here is the full solution in Java. You can pause the video here to take a closer look at the implementation. Notice it uses a slightly more compact way to calculate the prefix sum by updating the difference matrix in place. Next up, here is the C++ version of the solution. Again, feel free to pause and review the code. The logic is identical to the Python version we broke down. And finally, here is the solution in JavaScript. Hopefully seeing it in a few different languages helps solidify the concepts. So let's wrap it up. The biggest lesson here is that for problems involving updates over a range, or in this case a rectangle, the brute force method is rarely the best answer. The difference array technique is a classic powerful tool to have in your problem-solving toolkit. It lets you record all the updates very quickly, and then the prefix sum calculation lets you build the final result in a single efficient pass. Alright, before we jump into the other languages, I want to quickly show you a personal project I built to solve a problem that always drove me crazy. It's an app called My Daily To-Do. My biggest frustration with every other to-do app was retyping the same things every single day. Go to the gym, review code, work on the daily Leetcode problem. You know the drill. So I built my app around one simple but powerful idea: separating your routine tasks from your one-off tasks. Routine tasks, marked with the little refresh icon, automatically reset for the next day. One-off tasks, like ship new feature, get the little puff of smoke icon, and they disappear for good once you're done. This small change turns a dumb checklist into a smart scheduler. If that sounds useful, you can try it right now on the web. The link is in the description. And one more thing I want to make super clear. Right now, as a thank you for being an early supporter, the app is 100% free. There are no ads and no subscriptions whatsoever. This means you get access to everything, including really powerful features like presets, which let you save entire task lists and load them with a single tap. Now down the road, creating new presets will likely become part of a premium plan to help support the channel. But, and this is the important part, any presets you create now, while it's all free, are yours to keep and use forever. So it's the perfect time to check it out on the web, play with all the features, and build out your perfect setup at no cost. If you enjoyed this problem and want to keep practicing, the learning doesn't have to stop here. I've organized all my video solutions into handy playlists. Whether you're looking to grind through more Leetcode easy, medium, or hard problems, or you want to master a specific topic like sliding window or dynamic programming, I've got a playlist for you. It's the perfect way to focus your study sessions. Go to the Playlist tab and find a playlist that fits your goals. Also, if you're looking for even more Leetcode problems beyond the daily challenge, I've started a second channel called Leetcode Unlocked. It's where I'll be posting solutions to a ton of other problems, so if you're serious about your interview prep, be sure to check it out. The link is in the description below. Hope this Leetcode solution breakdown made sense. If it helped, give that like button a click, maybe subscribe for more, or drop a comment if you have questions. Make sure to turn on the notification bell so you know straight away when I upload a video, because I upload videos daily. If you want to support the channel, a few people have asked how I plan my solutions. I'm a big fan of sketching out the logic and data structures on a tablet before I code. It really helps. I've put affiliate links in the description to the tablet I use and a few other good options. Using those links doesn't cost you anything extra but really helps me out. Or, if you're feeling generous, there's always the Boba Fund. Keep coding and I'll catch you in the next one.